Hello, everyone. This is Dr. Kuo, and this is the first of our lecture series on chemistry review. So our bodies are made up of chemicals and matters. In order to understand how our bodies work, it's essential to have a basic understanding of chemistry. And that's why much of our first unit will be dedicated to reviewing chemical concepts. And in later units, it will become clear to you why these concepts are important in understanding physiology. Everything in this universe is either matter or energy. Our nature is filled with different substances with many different properties. So the philosophical question that naturally arose was, if we keep cutting something into smaller and smaller chunks, whether it would still retain its property, or would it become something else? And from this thought process arose the concept of an atom. If you smash a gold atom, you will no longer have gold. And so an element is a substance that cannot be broken down chemically into any other substance, an atom being the smallest form of an element. Out of all the elements found on Earth, only about 25 are actually found in your body. And the top 10 most common of these make up about 99.9% of your body. And just 4 elements make up more than 96% of your body. Okay. And those big 4 are oxygen, carbon, hydrogen, and nitrogen. Okay, again, oxygen, carbon, hydrogen, and nitrogen. And so with the knowledge about the big 4, you can understand a huge amount about nutrition and physiology, or just how your body works. So we'll be looking at the property of these 4 elements later. Here's the periodic table of elements that hopefully all of you have seen, and make sure you can correctly identify the chemical symbols for the elements listed here. So take a moment to pause this video and make sure you can find these. You got hydrogen, carbon, nitrogen, oxygen, sodium, magnesium, potassium, calcium. We've got phosphorus. Okay, we got sulfur, chloride. Okay, and so those are the important ones. Oh, iron is also pretty important. Okay. Just a quick reminder as to how to read the periodic table. So each element has a symbol or abbreviation of the element's name. And then you'll also see the atomic number, which represents the number of protons that can be found in the atom's nucleus. And then we also have the full element name and atomic mass, which is the combined mass of the atom's protons plus the neutrons. All atoms, whether it's an element of gold or element of oxygen or aluminum or whatever, they all have a basic structure that they follow. At the center of the atom is the nucleus, which is made up of 2 types of particles, protons and neutrons. Okay, and these are of similar weight. Okay, whereas electrons are much lighter. Protons being positively charged, neutrons are does not have a net charge. Electrons are negatively charged. Okay, and it's the protons. Remember, it's the protons that define the element. Okay, and it's represented in the atomic number of an element. If you increase the number of protons or decrease the number of protons, you're going to change the element to a different element. Okay, so it's by changing the atomic number or the number of protons that we change one element to another. Okay. Now, when you look at a diagram like this, you may be confused as to why all these positive charges in the nucleus are able to bind to one another. Okay, so confusion is a normal part of learning process. And through this process, I want you to ask questions, even though um, some of the students who are watching this video may be part of the asynchronous class. And so bring your questions to class, okay? When they arise. So I want to take a moment to explain what we're seeing here. So the nucleus of an atom is held together by a strong nuclear force that binds together protons and neutrons. Although the strong nuclear force is the strongest of the four fundamental forces, it can only act over very short distances. Okay, so typically nuclear distances. It binds together the protons and neutrons in the nucleus. So that cloud of electrons surrounding the nucleus are negatively charged. Okay, and the electron weighs almost nothing, less than 1/12 or 1/20th of a percent of the weight of a proton. Particles that have the same charge will repel each other, and those with opposite charge will attract one another. Because electrons all have the same charge, electrons in an atom all repel each other. And because they're negatively charged, they're attracted to the positively charged proton in the nucleus. So this attraction holds electrons close enough to the nucleus to keep them from flying away, while the energy of their fast movement keeps them from collapsing into the nucleus. So make sure you can draw the atomic structure of the commonly found elements in our body. So the atomic number for nitrogen is 7, for example. The average weight of nitrogen is 14, and that tells us that on average, most nitrogens have about 7 neutrons. Okay, that's 14 minus 7. Okay, and here, take a moment to see if you can draw the atomic structure for nitrogen. The atoms don't always have the same exact number of don't always have exactly the same number for protons as they do neutrons. Okay, and when they lose protons or gain protons, they become completely different elements. But when they lose or gain neutrons, they actually stay the same element and become what's known as an isotope. Okay, an isotope of that element. Okay. And when atoms gain or lose electrons, they become ions. Okay, positively or negatively charged ions of the same element. Okay, so once again, when you lose or gain protons, you become a different element. If you lose or gain neutrons, you become an isotope of the same element. If you lose or gain electrons, you become ions of that same element. So an atom's charge doesn't change in an isotope because neutrons have no net electrical charge. But adding and subtracting the neutrons will change the atom's mass. Okay. For example, in the case of carbon, okay, isotope 13, carbon 13, okay, has an additional neutron. So that increases the atomic mass to 13. Carbon 14, likewise, would have a heavier atomic mass compared to carbon 12 and carbon 13. And as we just mentioned, normally an atom has the same number of electrons as they do protons, but with additional or less electrons, the element becomes an ion. So cations are positively charged, anions are negatively charged. And because of their electrical charge, ions behave very differently from the atoms that give rise to them. Atoms can bond together to form molecules or compounds. Molecules are groups of atoms held together by chemical bonds. Okay, and whereas compounds are molecules consisting of two or more different kinds of atoms. And make sure you recognize that not all molecules are compounds. An example is the oxygen, diatomic oxygen. Oxygen in our nature exists as an oxygen molecule, two oxygen atoms bonded to one another. Okay, and so that's a case where it's a molecule because we got two atoms held together, two oxygen molecules held together. But because the oxygen molecule is made up of only one type of atom, it would not classify as a compound. Okay. Here, this illustrates different ways of representing molecular structure. Okay, make sure you are familiar with all these. And a concept that you probably already learned before that we will be revisiting this semester is that you can see chemical bonds as short-term storage of energy. Okay, when bonds are built, that requires energy, and when bonds are broken, energy is released. Okay, and so in that sense, molecules are created as short-term storage of energy that can be harnessed later. Well, the number of protons is what defines an element. It's the atom's electrons that really determines how or whether or not it will bond with other atoms. Electrons move very quickly, and so it's impossible to determine at any given moment exactly where they are. Electrons are not just moving about haphazardly, they actually are speeding around the nucleus with the tendency to stay within a prescribed area. And that area is called an electron shell. Okay. An atom may have several shells, each occupied by its own set of electrons. And within a shell, the electrons will try to stay far apart because their negative charges will repel one another. And so this first electron shell is closest to the nucleus and can hold 2 electrons. The second shell can hold 8 electrons. Third shell can hold up to 18 electrons. And atoms, they become stable when their outermost shell is filled to the capacity. Okay, and for other atoms, okay, such as those on the first column of the periodic table of elements, sometimes they will actually lose an electron to achieve these perfect numbers. Okay. In this diagram, we can see that stable atoms like helium and neon, these elements are a lot less likely to react with other elements or atoms because they are content with the outermost electron shell filled. Okay. In the case of other elements, okay, the way they react is according to the vacancies in their outermost electron shell. Okay, and they're going to react in such a way so that they can try to fill those electron shells. Recall from your chemistry class that there are 3 principal types of chemical bonds. We've got covalent bonds, ionic bonds, and hydrogen bonds. Covalent bonds are strong bonds that are formed when 2 atoms are sharing electrons. Ionic bonds is the type of linkage formed from the electrostatic attraction between oppositely charged ions in a chemical compound. And that kind of bond is formed when the valence shell electrons or the outermost shell electrons of one atom are transferred permanently to another atom. An example of that is sodium chloride. Sodium has one valence electron, and so in reacting with chloride, it completely transfers or permanently transfers its valence electron to chloride, and that completes the valence shell of chloride, while also making sodium achieve a full valence shell. Okay. Hydrogen bond is a type of weak bond between two molecules resulting from an electrostatic attraction between the protons in one molecule and an electronegative atom in another molecule. Okay, and in really large molecules, hydrogen bond can actually occur within the same molecule. Okay, and that's something we're going to see later in this class or later in this semester in the case of understanding how proteins fold and also how DNA forms their helix. Okay. So once again, covalent bonds is where strong bonds formed when two atoms are sharing electrons. And the example given here is the covalent bond existing between two atoms of hydrogen, okay, to form this hydrogen H2 molecule. Okay, this is a case where we've got two identical atoms, two identical elements sharing electrons, and so the electrical charge and the electron cloud will be shared equally. But there are cases where the covalent bond is formed between two different types of elements, two different types of atoms, and that may cause the electrons to be pulled closer toward one atom than another. Okay. Now, when it comes to physiology, you're going to hear us talk quite a bit about carbon. And carbon, with its versatility, allows it to bond with many different other elements. And that versatility is based on the fact that carbon has 6 electrons overall, 2 in the first electron shell and 4 in the second electron shell. And because the second electron shell has a capacity of 8 electrons, carbon can share its 4 electrons in its outermost shell, in its valence shell. Okay. And so this gives it an ability to bond with other atoms in a large number of different ways, including in 4 different directions, and making up a huge variety of complex molecules possible. In our body, carbon most commonly bonds with oxygen, hydrogen, and nitrogen. And because carbon atoms often bind to other carbon atoms, carbon chains are very common in our body. Okay, and each carbon bond to 2 other carbon atoms can still bind with 1 or 2 additional atoms. These carbon chains are present in most organic molecules. Okay, and so here we see examples of these organic molecules, proteins, and different types of sugars that make up our body. So here's a diagram that shows that carbon with its 4 valence electrons, when it reacts with 4 hydrogen atoms, it can share its 4 valence shell electrons, and in sharing those with those hydrogens, hydrogen is happy because they attain the full valence shell because the first shell can contain 2 electrons. Now with the sharing, hydrogen, each of these hydrogen now has 2 valence electrons, and the second shell in carbon being able to accommodate up to 8, okay, is also happy because with this sharing with hydrogen, it's also able to attain its ideal full valence shell. When you have 2 electron pairs that are shared between atoms, double bonds occur, and you can actually have more than just 2. When 3 electron pairs are shared, we can have triple bonds. Okay, and so in the case of oxygen atom, oxygen has 8 protons, 8 neutrons, 8 electrons, and of the 8 electrons, 2 occupy the first shell and 6 occupy the second shell. And so the second shell can fill up to 8. So when 2 oxygen atoms are near one another, they're going to want to react in such a way that they form a double bond. And when they form a double bond, that's how both oxygen atoms are able to be happy with their filled valence shell electron. Okay. In the case of nitrogen, nitrogen has a valence of 5 electrons. Okay, and so it needs 3 in order for it to be happy. Okay, because it wants to attain 8. Okay, and so when it reacts with another nitrogen atom, it's going to form a triple bond. And in forming that triple bond, now 3 electron pairs are shared, and each of them can now attain their filled valence electron shell. Now, not all covalent bonds are the same. Some covalent bonds are nonpolar, such as the case in this hydrogen molecule, where 2 of the same type of atom react with one another, and so the electrons surrounding them are shared equally between them. There are also cases where we have polar covalent bonds, where one element or one atom is more electronegative or has a stronger tug or pull of the electron than the other. And so such is the case shown here with hydrochloride or hydrochloric acid, where we see that the chloride being more electron negative is going to have a stronger pull of the electron cloud shared between them. Okay, and so it doesn't completely rob hydrogen of its electron, but it has a stronger pull of the electrons toward it, and so there's an equal share of that electron, creating a polar bond. Okay, and we can say that the bond is a dipole or has a dipole moment, meaning that the bond has a positive end and a negative end. The more positive or the more negative atom in a bond is often shown with the delta negative symbol. That means partially negatively charged. It's not a full negative charge. And a more positive atom is shown with the delta positive symbol. Unlike the stronger ionic and covalent bonds, hydrogen bonds are actually more like attractions than true bonds. And they tend to form when a hydrogen atom already covalently bond to one electronegative atom, okay, is attracted by another electron-hungry atom. So there's a bridge that forms between them. Okay, not a permanent bond, but rather it's a transient connection, transient attraction. So here we can see that oxygen, with its more protons compared to hydrogen, its nucleus containing more protons, meaning more positively charged, is able to tug and pull the electrons harder than the hydrogen atoms can. Okay, and so when the two form a bond, the electron cloud will be pulled more toward the oxygen than toward the hydrogen. Okay, and so such is the case in a water molecule. Okay, and so what this means is it results in a molecule where there's a dipole. There's a slightly partially negatively charged end toward the oxygen, and there's a partially positively charged end toward the hydrogens. And hydrogen bonds are formed between the slightly positively charged hydrogen atoms of one molecule, okay, and the slightly negatively charged oxygen atom of another water molecule. Hydrogen bonding is responsible for the tendency of water molecules to cling together and form films referred to as surface tension. And this tendency helps explain why water beats up into spheres when it sits on a hard surface, and just why water striders can walk on a pond's surface. Okay. Although hydrogen bonds are too weak to bind atoms together to form molecules, they're actually very important intramolecular bonds, intramolecular forces that hold up different parts of a single large molecule into a specific three-dimensional shape. And so many of the important biological molecules in our body, different proteins, different sugar molecules, okay, they're able to attain a specific three-dimensional structure thanks to hydrogen bonds. Okay, so even though individual hydrogen bonds are fairly weak, across a large molecule, they can actually create a significant force that determines the three-dimensional structure of a large molecule. As we've mentioned, hydrogen bonds can be intramolecular or intermolecular. Inter is in between different molecules. Intra is within the molecule. Okay, so here's intermolecular examples of hydrogen bonding between different molecules of water. And here is an example of intramolecular hydrogen bonding occurring between different parts of a single peptide chain molecule. Okay. An ionic bond is an extreme case of polar covalent bond. In an ionic bond, the bonding atoms differ so markedly in their attraction for electrons that one or more electrons are essentially transferred from one atom to the other. Such is the case in sodium chloride. Sodium chloride bond is an example of ionic bond. The attraction of the chlorine atom for electrons is so much greater than that of the sodium atom, such that we see the valence shell electron in the sodium is being completely transferred over to chloride. Okay, and this results in two oppositely charged ions. Sodium now becomes or has attained a +1 charge. Chloride now has a -1 charge, but both have actually now attained a full valence shell electron. Sodium in losing one from its third shell, okay, which only had one electron to begin with, now has a full second shell, or its outermost shell. Chloride, okay, used to have a vacancy in its valence shell, is now filled with the electron that it's accepted from sodium. So take a moment to review the three types of bonds that we discussed in this lecture, and make sure you understand and can give examples of these different types of bonds.